Okay, thank you very much for the introduction, Mark. Yeah, as he said, my name is Isabel Orff. I'm one of the metabolomic scientists at Alzone, working on the liver projects. The title of my talk today is Breath Limonene and Liver Disease. So you already see the connection to Chris's talk from this morning. So we're trying to use EVOC probes, and I'm going a bit more into detail about what we mean with this term to assess metabolic pathways. But going a bit back to what are we actually trying to achieve at Alzone. So we didn't mention it before today, I think, but our big mission and vision is really to save lives through early detection of diseases, but also we have quite a lot of research going into precision medicine. In the liver space, we're actually covering both sides of the mission. However, today I'm going to focus mostly on the early detection. Now, if I talk about liver diseases, what do I actually mean? Liver diseases is a quite complicated space, I would say. I'm not going through every detail on this slide, but hinting you at some of the important bits. So we start off with a healthy liver. Hopefully most of us are at this state at the moment, but there is certain risk factors like obesity or diabetes that might lead to deposition of fat in your liver. So you will then have a so-called non-alcoholic fatty liver. So the disease is called NAFLD. With increasing fat deposition over time, this can lead to inflammation, so you move into a state called NASH, or non-alcoholic steatohepatitis. Now, at these points, everything is still pretty good. You will probably not feel anything. The doctor will not see anything when you come in for a regular visit. But at that point, you can actually develop fibrosis and scarring. And then this can lead to cirrhosis, which is a much more tricky condition. Up to this point, all of these stages are reversible, so especially for example, an obese patient with NASH, you would recommend a healthier diet, you would recommend a better lifestyle, and this person could really regress to normal. But at some point in cirrhosis, you get into the decompensated state, and that's quite a problem because from that point, that actually leads into liver failure or into the development of cancer that is called hepatocellular cancer. Now, just one note, cancer is always a tricky topic. You can actually develop it also without having cirrhosis before. So there is the unlucky cases that end up here without going through all of this pathway. And the question is, of course, like how important is that? We had that before. Obviously, if I'm interested, it's likely very important. So this is just a one-sentence quote that I picked from the internet from a report from last year, where it was estimated that in the US, currently, NAFLD affects roughly 100 million Americans, and it already costs the healthcare system about $32 billion. Now, you know, the projection is we will have more people in the world, and we will also have more obese people in the industry world, so in the first world states. So this is likely going to explode. What are we going to do to tackle this? There's obviously two things. One, we need good treatment, but the other thing is also we need good diagnostic tools. So the question is, what do we currently use to diagnose it? So we have a bunch of different tests. There is the typical liver enzyme test. So this is mostly proteins measured on your blood. There is ultrasound and CT, so that's imaging techniques. There's the more invasive liver biopsy, so actually taking a piece out of the liver, looking at the tissue, seeing what changed in the tissue in contrast to a healthy tissue. And there is a bit more modern techniques like this transient elastography, which is actually also an imaging technique. Some people might know it as FibroScan. So it looks beautiful. We have several techniques. However, there's drawbacks to these techniques. So the liver enzymes, they claim they are a liver function test. Now, I really have a problem with that because what we're actually measuring is not the function, it is parts of the liver dying, it is liver damage. So it has nothing to do with function. When we look at all the imaging techniques, they're beautiful because they're non-invasive, but they're also very indirect. So, I mean, you're getting a picture, you can make some assumptions about it, but you're not getting any direct value from the liver. Liver biopsy obviously gives you that, but as I said before, it's very invasive. It's currently the gold standard, but it's localized. You can imagine the liver is like not a tiny organ, so if you take out a 1 centimeter, 2 centimeter piece, you might just miss the spot where the cirrhosis started. So that's problematic. So in conclusion, we have currently no single test that actually gives us reliable function data for the liver. And we're hoping that we can get into that space with our breath test. Now, this audience might not be so surprised why we're looking for biomarkers for liver disease in breath, but when we go to other meetings, that's like a really common question, like, but it's the liver, why do you look on breath? So this is something that is not new. So Chris mentioned it also this morning, there's this Fetor hepaticus. It has a Latin name, so I'm guessing it's quite ancient. But the first publication that I found mentioning it is from 1946. It's called The Breath of the Dead, and it's a very strong, musty smell. Now, this paper that I screenshotted here is from 1955, and I think it's the first mentioning of actual compounds that they measured that could be responsible for this smell. Later, it turned out that it's probably not the advanced, so not the liver itself that does this, but the very common side effect of having this secondary pathology, portal hypertension, and this leads to sulfur-containing compounds being released into your blood and then end up on your breath. But there's, of course, also newer evidence, referring back again to Chris' talk from this morning. So his group had a look at patients with also advanced liver cirrhosis and liver cancer. So they were, I think most of them were waiting for a transplant. And they had quite interesting results because they found the this compound limonene being increased in the patients. And even more interestingly, it went back to normal after the transplant. So this is a very clear evidence that the signal is really coming from the liver, right? I take the organ out, replace it with something new, and the signal is gone, so it can't get much clearer. So we thought this is very interesting, and we also thought it is especially interesting that this is not the typical endogenous compound that we would classically look for when we look for biomarkers. Just to bring that up again, so most people, when we look for biomarkers of diseases, we obviously look for compounds that come from processes that happen in the body, right, that are produced by our body. So we look for endogenous volatile organic compound sources. But we think there is good evidence in the literature and also in our own studies that you can actually use compounds that are not coming from the human itself, but that are ingested, that we get through environmental exposure, through medication we're taking, our diet, if we're smoking or not, how much exercise we do, or even the composition of our microbiome. And they might give us still very reliable signals about processes in the body because our body still uses those compounds, metabolizes them, detoxifies them, and tries to get rid of them. At Alston, we call this the Exogenous VOC, EVOC probe approach. So what we do is, or what we're trying to do is we're administering compounds, pure compounds, to a patient or to a person. And these compounds are known beforehand to be metabolized by a specific enzyme. So what we're trying to do is really targeting that enzyme and get a readout about the function, about the activity of that enzyme. This obviously requires quite a lot of a priori understanding of the disease mechanisms, and that's what most people in the team I'm working in are involved in. So we're reading a lot of papers, we're trying to understand everything and make the connections for the metabolic pathways. The beauty of this, though, is if I have a single compound or 3 compounds that I really want to look at, then I can of course use the targeted approach that Kaylee also covered in her talk. I will bring up another slide about that in a minute. This is another summary slide for our EVOC approach. So basically, this picture gives you the visual summary. You give the patient something, it is metabolized, and you measure ideally the substrate itself and the products. And then you can link that to the enzyme function, enzyme activity. What else is nice about using exogenous compounds? Well, it is still completely non-invasive. If we do it that way, we can administer a cocktail of probes, so we could at the same time measure the activity of several enzymes. The probes we're currently looking at are all food-derived, so we don't have many requirements from a regulatory point of view. That's very good. And because of that origin, they're also rather low in cost. So looks like a quite beautiful approach, right? But so before we wanted to go and test limonene as an EVOC probe, we thought it would be worthwhile to do some external validation of the study that was done in Chris Mayhew's lab. And so we started a collaboration with him for a pilot study where we planned to not only validate his results, but also try to bring the whole thing to a bit of an earlier disease stage, so basically go from advanced cirrhosis into earlier cirrhosis stages to see if the signal tracks with severity of the disease. We also, even though we're doing a targeted analysis in this case, still wanted to have a bit of a look into other biomarkers, so we're going to do that I think starting next week with the data that we collected. And yeah, this one I already mentioned, wanted to look if it tracks with severity. Just to sum up the study, it's a pilot study, it's a small study. So you will see that in the data as well. There's clear implications for increasing the numbers, but currently we look at 3 groups. We look at cirrhosis, liver cancer, and healthy controls, and it's 15 subjects per group for this first pilot study. All our participants are over 30 years old, and our groups are matched for age, gender, and known risk factors. Initially, we wanted to compare both disease groups to healthy controls, so that's what I'm going to show you in a minute. And we're excluding patients that have both cancer and very severe cirrhosis because we think it would just, disturb the signal, make it very unclear to separate the two. Yes, so back to the question, when do we do discovery, when do we do targeted? So discovery is really something that is necessary if you have no idea what you're looking for. If you just know this is a disease that I want to look at, I want to find a biomarker for this, I might have some vague idea of which pathways, then I can maybe go into the direction, say I'm looking for a certain compound classes. But if I want to do a targeted approach, I need to have a clear idea of what I'm looking for. In this case, we have that. We have limonene, so it's a promising biomarker. So we developed an analytical method and a data analysis method that are optimized for this target. When we do this, we can also include calibration curves, which then allow us to quantify the compound as well. And this study was also a first nice use case for our orbit traps. What we were expecting is very, very varying levels of limonene, so very low values in the controls, very high values in the disease groups. So in order to reliably measure that, you need an instrument with a high linear dynamic range, and we think the orbit trap is perfectly suited for that. Of course, it has other advantages, but this is really the main reason here to use the Orbitrap system. Now, if we, this looks very similar to some of the plots Kaylee showed you this morning. We did the validation, of course, for our method also for limonene. If you look here at 2 calibration curves, we're really near perfect linearity over the range here of 0 to 300 nanograms of nanograms on tube of limonene. And this is 2 calibration curves, 1 run before our breath sequence, 1 run after, so it's very stable. We did also the several injections of the same concentration to see if we always end up with the same signal, and this is pretty much the case. We have an average accuracy of over 90% here. So that's very beautiful. We did all our prep, so let's have a look at the first results. So this is a simple box plot of limonene levels in the 3 groups. As you see here, we're not quite there even with our 15, 15, 15, but I know the samples already arrived at Austin, so we're going to be there very soon. And what you can clearly see here is that we have increased levels of limonene in both disease groups. Now, I forgot to plot this here, but both the comparison to the healthy control are highly significant. That's, of course, very nice, and that confirms what Chris saw in his study. Now, another thing that you might realize is that there's quite a big box here for both. And what does this mean? That means that we have quite a range of levels. Now, the question is, of course, why is this the case? And I would like to remind you that what we did in this small study is we included people with different severity. So we thought, well, let's have a look if these levels track with measures of disease severity. So what we did is we plotted them against 2 different scores for liver disease severity. The first one is the so-called Child-Pugh score. That's a nominal score, so you get a score based on certain underlying factors, and then you're either class A, B, or C. Correlation, very poor. But there is some hope. So we thought, well, let's look a bit further. Also, I mean, reminding you, we don't have that many samples. And then we went on and plotted it against this score. This is called MELD in the US. In the UK, we have a little tweak to that system, so it's called UCALD. But what we see is that the correlation with this score is much better, so we have around 0.7 R² here. By the way, I'm sorry. I'm focusing only on the liver cirrhosis patients here. So the cancer patients is a different story. Wait for that at a different time point. Yeah. So this is very interesting. So we see some correlation with the severity of the disease. And obviously, I said this is a very small group, so we really want to expand that to more patients and really see if that holds true and where we get with this. But we had a bit of a look also at the underlying factors. So what we did is we plotted limonene in the cirrhotic patients against different measures, for example, the liver enzymes. And as I said before, the liver enzymes are claimed to be a function test, but I don't really would like to call it like that. So what we saw is that limonene plotted against AST, ALT, these liver enzymes, gives us absolutely nothing. But when we plot it against bilirubin, we actually see something. Whoops. Sorry. Missed the spot. We actually see again something that looks like a correlation. It is R² is 0.52. So a nice promising first result. We hope to add more data to this. Now, why am I so excited about this? This is because bilirubin is one of the few measures that we have that actually are a functional assay. So what we can say now is not only does limonene seem to correlate with the severity of the disease, but it also seems to correlate with other measures of liver function. So it seems to be really the biomarker we are looking for. Now, as you see, there is quite some variation around, and we have some outliers. So obviously, we also look into other factors that contribute to our signal. One of the possibilities in terms of liver disease is to look at the gender of the patients. Liver disease is still something that is more abundant in the male population and the female population, and we generally have males with more severe disease. But it is quite interesting because we have females that have a similar Child-Pugh score and they seem to all cluster here in the lower levels, whereas for the males we have at least this one that has a quite extreme value. Obviously, again, I have very few samples in this plot, but let's see what happens when we sample more people. So we're going to keep looking at this to be sure that we're not misinterpreting some of our results. Another thing is, of course, limonene, as I said, is an exogenous compound, so we take it up through food. So we asked our patients, how often do you drink orange juice? How often do you eat fruit? And there is quite a difference between the ones that eat it daily and the ones that don't. So this is obviously a factor that we need to take into account, at least for this specific study. But we think that it is also a perfect reason to start looking into our EVOC approach, because if we administer something at a given concentration, then everyone has the exposure. So this will allow us to overcome this issue. So with this, I come to our next step. Obviously, first one, continue recruitment. It looks promising, so we really want to add more patients to this study and really see if it holds true and where we can go with this. We also want to expand our analysis to other compounds, so we think it's quite straightforward to look into other terpenes. They should be captured even in our targeted method, so we just look a bit on the right and left side of limonene and try to extract compounds there and identify them. And the other thing is we really want to go and, in a next study, challenge patients with earlier stages with our limonene as a probe. So we think that this allows us to see differences even in, for example, NASH, to be proven because we don't have samples there yet. But we also really think that this gets our exposure problem straight and removes this difference that we're seeing there at the moment. Yes, and with this I'm already coming to the end. Have a lot of people to thank here because this is a study integrated in a quite big trial that we're running with the NHS. So first of all, I want to thank people at Alston. So this is like the chemistry team, it's the team or the test team that helps with developing these things into actual tests. A lot of people from the clinical sciences and clinical trials team that help with cleaning data labels and pulling the data from our patient database. But then I also want to thank the people in the PAN study, which are the doctors that actually recruit the patients in their clinics, Rebecca Fitzgerald being the PI on this study. And I also want to thank the people that work for us at Addenbrooke's, really helping us with getting all the information. And I saw that some of you are here, so great to see you. Yeah, and with this, would like to thank you, and I'm happy to take questions.
We'll go back and forth. Thank you for that, Isabel. I'm sure there will be loads of questions. I'm going to start there. Please announce your name and ask your question.
Oops. Yeah, now we have two. Yeah.
Can you hear me okay?
Yeah.
Did I see, interpret this right, that there's a dietary component to the limonene excretion? If so, do you know what that is and how long it persists for?
So we have a other study in-house where we already give, where we try our EVOC approach. So there we have healthy people drinking a lot of orange juice, for example, and we look how long that signal lasts. And for a healthy person, they will clear the signal in about 3 hours. So in case of the liver patients, this is of course a different story because there we think, or what we're seeing is the accumulation over time because the liver cannot detoxify limonene or cannot metabolize it, so it will linger around. So it is more extreme in this situation because the condition just gives you the signal.
I'm Robert Rintoul. I'm a chest physician, actually, so I don't know much about things below the diaphragm. But in the figure you showed about limonene levels in normals and HCC and cirrhotics, the patients with HCC, were they all pre-cirrhotic?
No, so we're looking into this at the moment. We have some of them with cirrhosis and some without. And obviously we want to see how the limonene reacts in them based on that. We got the last data over the weekend, so we're getting there to
The reason I ask is because they
this.
look very similar.
Currently they look very similar,
And I just wondered actually
yes.
if you really were measuring HCC or actually just measuring two slightly different groups of cirrhotics, because HCCs can be quite small or they can be very big.
Yeah,
so then you'd have to look at it by stage as well.
Exactly.
Which
so
is
we're
tricky
looking,
given the numbers you currently have, but
Yeah.
you've clearly factored that in.
Yeah, so we have the staging, we have the node size and all these things, so we're going to take that into account, yeah.
Great. Anil?
Following up on this question, the HCC may not be the ideal set of subjects that you want to include in this population unless they have cirrhosis, accompanying cirrhosis, because HCC is very localized. It could be a very small portion of the liver, and normally resection is done in a very small portion of the liver for that reason. Because carcinoma is not throughout the liver. Cirrhosis is throughout the liver, and so is fibrosis. So maybe the HCC population, unless they have cirrhosis along with HCC, you shouldn't include those, because then you'll see outliers.
Yes.
Because their function is still perfect. They still have 100% liver function, even though they have an HCC, a localized tumor.
Yes. So the study I was doing is obviously a cancer study. So this is the primary reason to have them in there. But also I think it's very important to compare, conditions that are quite close to each other, because there is still a lot of cancer developing out of the cirrhosis. So to see what would be a differential signal, if it's not limonene, that's okay. But we wanted to see how the signal looks like.
Okay, time for one final very brief question.
In terms of liver function tests, say a caffeine clearance test, do you have any data comparing the D-limonene levels with the liver function test?
Not yet. I really, really would like to include that in the next study, yes.
Thank you so much for the presentation and addressing the questions. I'd like to introduce